Hello everyone, welcome to the P1 Classical Mechanics program. So this lecture is called P103. In this lecture, we are going to handle the estimation of errors. So we are going to discuss errors and uncertainties in measurement. So basically, if you are using the word error, which means that you are mentioning some kind of a mistake that you made. So in physics, an error is not actually a mistake, okay, in this sense of uncertainty. So there is, if you consider a measurement, say that you are measuring the pendulum which is swinging back and forth, and you can see that the bob is swinging from this side to this side and then comes back, and the time taken for that bob to return, the time can be measured, right? So if you measure the time, say 3 seconds, then you can say that there is an error in your measurement, because what I mean by an error is that you have an uncertainty in your measurement, that you're not sure with the percentage of uncertainty of say 0.1 seconds. So you cannot measure any better than that kind of a accuracy. So you cannot go accurate any more than that. That's basically what error means. So with this, if you say that I have a plot of say time versus number of experiments that I've taken with the case of the pendulum swinging back and forth, you say that each time I get a time limit, and the next time this, and so on and so forth. So you see that there is an inaccuracy in the measurement that you made. Your time value is fluctuating. With each measurement that you make, the time value is fluctuating about a fixed point. So you can experimentally take out the values, different values, say 3.3, 3.4, 3.6, and take the average of that, and the mean value can be calculated by dividing this with the number of iterations that you have taken, and you get a mean value. So that's mean value. And then there is deviation from your mean value. If this is your mean value, then there is deviation on either sides with a small extent. So this deviation is the bandwidth of your uncertainty. So your estimation is as accurate as within your bandwidth of accuracy, or it is called the uncertainty. So you say your calculation, if the mean value of this whole thing is say 3.4, you say your estimation is well within 0.2 seconds accurate. So that's for this typical calculation, it is as good as this. Now if you want to develop a standard way of representing the mean value, you can say that mean value can be considered as some limit x tends to infinity, say, or n tends to infinity, say x1 plus x2 plus etc up to xn by n. So that's a standard way of representing the mean value. This means that you took the average of all these numbers, and for all eternity, for all set of calculations that you've done, all set of measurements that you've done, the average value is the mean value. That's a typical way. Now you can define a deviation that we have mentioned. This deviation can be defined as sigma, which is stands for standard deviation. You can put limit x tends to or n tends to infinity, say square root of sigma of xi minus mu by n minus 1, because n tends to infinity, that's why n minus 1. Now from 1 to n, right, 1 to n, you can take this value and take the square of that. To avoid this square root of square means that you avoid all negative values. So negative values will be vanished from this system if you take the square and then the square root. So this clearly means that for each value that you measure, the difference between the mean value and the sum of the all those values and the square root of squares of that values, that means a positive deviation from the center, a positive deviation from the center on either sides. That's how you measure that. This is a statistical normal representation. So this can be used as a standard way of representing an uncertainty. So you can say it's 2 sigma is a standard notation for uncertainty, because we have to take for say, if you have this as the true value, means the accurate value, you have measured this value, this value, this value, that means there is a deviation on this side and also there is a deviation on this side. Now you can use this equation and find out this value of deviation sigma, and you see that the deviation is from center mean value to this value. Also there is a sigma here, so 2 sigma can clearly depict the depth of uncertainty in your measurement. So this is a statistical approach of handling an uncertainty. Okay, now if you consider an equation, let's say it's 3x cube plus 2x square plus 1x plus 5, this kind of an equation equal to 0, that's only when an equation is formed, right? So this, if this kind of an equation is considered, you will see that the plot might look bit wiggly, right? It will say go from, see, it will go something like this, something like this at 5, right? At 5, 0 here, because at 5 the values will be negative for certain domain. Say it will be around plus 3, the values will be negative because the third power quadratic term dominates for up to some point, and then afterwards the negative values, negative y values, turns positive because the rest of the powers will get to much better chance, right, after minus 3. Okay, so and then when it reaches 5, it will fluctuate because 5 is our constant point here, so it will fluctuate and will go up from there. Okay, so that's what going to happen with this kind of an equation. It's a quadratic equation. Now if you it's a polynomial equation. If you think that you are going to represent, this is the state of say something that you're going through a car and you're going from A to say B, and it's going to be in this kind of a shape, and you're going to accelerate. When you go from this point to that, you are going to accelerate and decelerate. You change your velocity, you may stop there, and your velocity time graph might look something like this. Okay, so there's no negative velocity if it is positive. Okay, let it not be negative. Let's avoid the negative values. If it's positive, in this positive sphere, you can say that at time t is equal to 0 around here, and before that and after that, okay, t is equal to 0 around here, before that and after that, this is what going to happen from here to here. So if this curve represents your velocity from traveling from A to B, then you can clearly see that there is a clear path of distribution for velocity in this set, right? But actually when you measure, you may make some kind of a mistake. Your car speedometer might make some kind of a small mistake. That means your speedometer will be a small part different from the actual value. So you have plotted this value based upon your preference, your actual estimation of a change in velocity, and you've decided that this would be my path, this would be my velocity time graph. But when you actually made this trudge, right, trucking, you will find that your velocity time graph is fluctuating in a tiny small manner, that it is not as same as we have expected. So is it well within your uncertainty is the question. Is it within your uncertainty? If it is within your uncertainty, then your measurement is okay. If it is not within your uncertainty like this, then you have made some changing criteria in your transverse motion. In your motion, you have made certain changes that fluctuated your graph, so you need additional data, additional equations, additional terms in this equation, some additional terms that is needed to comply with the plot. Now you need additional fitting, so you need additional terms to fit this curve to into a new form. If that's not the case, right, that's not the case, you're perfectly within reason to believe that your estimation is right. Even then you can see that there is a fluctuation, right? You have fluctuated from your path like this in a smaller way, in a very small way, okay, not this big of a difference, but well within 2 sigma. Okay, that's uncertainty, and that's the uncertainty bandwidth, and you have to be within the bandwidth of uncertainty. That's a sure thing. Now with that in mind, I'm going to give you simple tool how to measure the uncertainty. Like I have mentioned that when you measure the time, you will make a difference, a small uncertainty in your measurement. Say if you measure 3 seconds, you might make a uncertainty of around 0.1 second, because you are slow, you won't be that exactly as fast as how to synchronize your fingertips with the actual motion, and you will be off with the margin of 0.1 second. So you make that uncertainty. Now we have to take that into account of our calculations that we do in our everyday life. Okay, so that kind of an introduction of uncertainty is called error analysis. Okay, I have done almost a big brief introduction of all this. I hope it was worth it, and I'm going to give you a simple way to estimate the uncertainty or error. Okay, it's a poor man's method of solving uncertainty. Now for that, if you have like you measure the distance by time of a measurement, right? So distance by time, you say you traveled 400 meters in 10 seconds with an uncertainty of around 1 second, and with an uncertainty of distance around 20 meters. So this is around a 5% uncertainty, right? And this is around a 10% of uncertainty. So these two uncertainties are there. Now we have to take them into account. Now let's say, if with that in case, let's find out, okay, what would be the maximum difference from the estimation. That's the first thing to do when you are finding the uncertainty. So the maximum will be 420 uh, by by 9. That's the biggest value that you can get, right? So it's 420 by 9 will be around 46.7 something. Okay, it's not percentage, it's the speed, so it's velocity. Okay, and the minimum that you can get is 380, right? uh, 380 divided by 11, 11, right? 11, that will be giving you 34.5. So that's the minimum value, and this is the maximum value of velocity. So there is a bandwidth of difference with each of your estimation. Now which one do you consider, and what you are going to do, with it? So if you can clearly see that there is a 6 average of 6, approximately 6 difference in each one of them. So you can say it's 40 plus or minus 6, right? 40 plus or minus 6 is the velocity, average velocity, that you can estimate with maximum accuracy. You can see that this 6 means around 15 percentage of error, right? Uncertainty. That is not that unambiguous. You can see that this 5 percentage plus 10 percentage gives you 15 percentage, right? So that's straightforward. All you have to do is that when you do this kind of a calculation, you can clearly do is that add the percentage errors and you get 15, and you get the sum of errors, and you can directly do that. That's a simple easy way of doing it. Now let's do a bit complicated stuff, right? A by distance by time square, right? That has the dimensions of acceleration. Now if you do that, you get the same value, right? 400 plus or minus 20 by 10 plus or minus 1, right? And you do that again, you get 5 percentage and 10 percentage here, and you can say that b square, t square will be there, right? T square, that means there will be 20 percentage error. So you total you have to look for is 25 percentage. So it's 25 percentage is the total estimated error that you are going to have. So you will get, if you evaluate, you will get around 4.4 4 plus or minus, because 400 divided by 10 square is 100. So it's 4 plus or minus 1, that's 25 percentage, right? So that's the limit of accuracy. You can straightforward measure that. So that's an easy way of understanding error and how it propagates. So that's a very easy and obvious way of understanding error. Now if you look at a different thing, okay, I am going to give you the standard way of evaluating errors. Now say if you have a number, say a, right? And you add a number, a constant number with it. Okay, a has an uncertainty of delta a. So if you add a number without uncertainty, then you get a new number which has the uncertainty delta c, which is equal to the uncertainty of delta a. That's a standard way. Okay, that's one thing. Maybe if you want, I can do an example. You get 10.1 and you add say you have an uncertainty of say 0.1, and you get add 2, and you get the new number. uh, this is uncertainty. You get 12.1 plus or minus 0.1, so that the uncertainty doesn't change for C. And the second factor is, if you take, say, multiply a number with say n times a with an uncertainty of delta a for a, you get an uncertainty for delta c which is equal to n times delta a. So it's, so if you have 10 here multiplied with the 2 again, with the 10 has an uncertainty of plus or minus 0.1, you can see that you get 20 plus or minus 0.2, right? That's the uncertainty. That's how uncertainty propagates, the error propagates like that. Now if you have a third case, if you multiply something like a times b times c, the error will be, so delta c will be c times square root of delta a by a the whole square plus um, delta b by b b the whole square plus delta c by c the whole square. So that's how error propagates for multiplication. And you can also do this for division as well. You can say d e f, d times e times f, right? And if you do that, you only have to do is you can add this value to this. You can say delta times d by d, all you have to do is add, right? So that's how easy it is. E times e, and so on and so forth. Now that's how easily that you can find errors. Now I have covered almost all aspects: statistical, numerical, easy way of representing errors and how it propagates. Now I am going to use a real live example that we have taken earlier, like a bob swinging around a massless string. Okay, a string, it's swinging around, and I'm going to measure the time with uncertainty, and I'm going to find out how much uncertainty there is. Now for that, I'm going to take a 3-meter length bob, 3-meter length string, and there is a 100-gram bob attached to it. So the level of accuracy that I can measure is 3 meter, can be measured 3 plus or minus 0.01 meter, that is 1 centimeter accuracy. My meter stick is as accurate as 1 centimeter. Okay, 3 long meter. I could have made that kind of a mistake. Now along with that, if you I took this bob and I swinged it and I measured the time, right? I measured the time and I got a time of 3.5 seconds, and I had some lag with me. Maybe I should have made a mistake, an uncertainty of 0.1 seconds, right? So this is all I have. Now last lecture that we have mentioned that we have found out using dimensional analysis that a time for this bob to rotate will be equivalent to some constant time 2 pi, sorry, some constant time, sorry about that, some constant times L by g, right? So where L is the length and g is the acceleration due to gravity, which is around 9.8 meters per second on earth. Okay, so now we are going to use this and find out what c is. Okay, c is, use this principle. And for that, first I'm going to do is I'm going to substitute the values that I know, which is a 3.03 plus or minus 0.0, sorry about that, 0.1 meter divided by 9.8, right? So that's the uncertainty right there. So if you okay, we got that. Now I know this time taken for that, which is I measured the time here, so that's 3.5 into 3.5 into 5 plus or minus 0.1 second accurate. I got that all. Now c will be this times the reciprocal of that. Okay, this times the reciprocal of that. Now it has to go to the other side. I'm not going to do all that. Just I'll do the calculation in a rough sketch, and you get around 1.8. Okay, if you do this, you get around 1.8, and because it's 9.8 divided by 3 right there, and you have to multiply um, it by 3.5, and you get around 1.8 times. Okay, if you divide this, you get the reciprocal of that will be 1.8 plus there is an error in the denominator. That error can be written as 0.1 by 3, right? 0.1 divided by 3, the square root of square of that. You did in the last example. So that's that part, as in the reciprocal, times 3.5 plus or minus 0.1 second. If you do this as well, right? So you have to do it again, and you have to do it again with the, you have a multiplication factor here. Now you have to do it again also with, you have to add with 0.1 by 3.5, and you add with that and you get 6.3, 6.3, 1.8 into 3.5, 6.3 plus, you have to again add 0.1 by 3.5, the whole square, and you add that along with this and you get 0.05 plus or minus 0.05 is the constant value. So you have estimated a constant within the limit of an error, right? Now if you look closely, this corresponds to, if you are a mathematical expert, or even if you are not, you can see that 6.3 will be almost equivalent to 2 pi, right? So you can say that 2 pi, 1 pi is 3.14, 14 and goes on. So 2 times that will be 6.3, 6.289 something. So it will be approximately equal to 6.3. So we have clearly proved, okay, with a experiment that I have done personally. You can do it again, that c, so time will be equation of time for a pendulum oscillating around a fixed point with a massless string is will be around 2 pi times root L by G. Okay, so I've used certain principles I have explained earlier, and I have used the error analysis to estimate the error. This error is well within the limit, so it's very small. Okay, you can clearly see this is very small compared to that, so we don't need to bother about that. Error will get smaller when you have such a complicated transformation of multiplication or division. Error will get smaller. Error will get bigger if you have plus signs or subtractions. Okay, so that's the basis of error analysis. I hope I have covered almost all of those factors that you need to know to understand the basics, and I hope you enjoyed this session. And for more, keep watching. Okay, thank you.